Hello, everyone, and welcome to today's workshop. We will have the second day of this marine data for South America. This is a Copernicus Marine Service workshop, and today we will have a practical session. Yesterday, we gave you an introduction to the Copernicus Marine Service, what sort of data you can find in the service, what we provide in terms of global data. And we also provided some examples on how you can use the data considering local studies in South America. Today we will have a more practical session. So we will show you how you can visualize the data sets, how you can apply it or in specific to a case study. Before we start, I will give you some guidelines, so just a few house rules so that you can enjoy this workshop in the best possible way. You will notice at the bottom bar of this screen, of this live session screen, that you will find the globe symbol, an icon. That means you can select the language that you want to hear this session in. We have two amazing interpreters with us today, and they will be translating everything we will be presenting into Spanish language. So go ahead and click on that globe icon if you want to switch to Spanish. Okay, another little rule is we normally use the chat on the right side of your screen for small talk or for some technical issue you might have. You can use this tab for these situations. If you have a question directly to any of our speakers today, please use the Q&A tab you will find at the top bar of the events page. And you can post your questions there if it is anything related to our specific presentations. So today, as I said, is a practical session. You might have explored already all the materials we made available for you and the specific exercises that were developed for the topic we will present you today. As you can see at the top bar, you will find two tabs, one dedicated to the Jupyter notebooks and another one dedicated to the QGIS exercise. I hope you had the time to explore these exercises and have now some questions for our Stefania and Alvaro who developed these exercises. So just to give you an overview of what we're going to do today, we're going to start with a little demonstration of the MyOceanViewer given by Gaël Durand from Mercator Ocean International. You will be able to see how to access the Copernicus Marine data and how to visualize it. And then we will have two presentations by Álvaro de Pascual Collard and Stefania Ciliberti, who will introduce you to the exercise they developed, and they are here to answer any of your questions. So without further ado, let's start with the first demonstration. Gaël, whenever you want. Welcome.
Thank you. So I'm going to share my screen. Is it okay for everyone?
Yeah, perfect.
Okay, good. So I'm Gaël from the user support team of the Copernicus Marine Service. And today I'm going to present the MyOceanViewer and its main functionalities. So when you are to access the MyOceanViewer, when you are on the main page of the Copernicus Marine Service, you just have to scroll until you find the dive into our digital ocean. So here you'll find the three MyOcean that we have, the MyOcean Learn for beginners, the MyOcean Lite, which allow some interaction, and the MyOcean Pro. So here you have the MyOcean Pro interface. First of all, as you can see here, you can change the projection by clicking on one of these arrows. So you have the North Pole projection and the South Pole projection. Here you have display layer of the seawater potential temperature. I know that because here you have the little hide that said that this layer is displayed. You can choose to display a layer, hide another one, and the one that is on top is going to be the one that is displayed. You can also click on the map and drag it around to move it using your mouse. You can also zoom in and out of the map with the wheel of your mouse. So today we are going to focus on the eastern part of the South Equatorial Pacific Current and the interaction between the current and the net primary projection. So to do so, we're going to have to add the current layer and the net primary projection layer. So to do so, we're going to click on Add Layers. Here you'll be redirected to the Copernicus Marine Data Store with a little bit less than 300 products. You have some categories here, the most popular product, the recently viewed, new in Copernicus, and some other categories. Just a bit of information, not all the data set can be displayed on the MyOceanViewer, such as the in situ and long track products, but this is going to change in the incoming weeks. So under each thumbnail for each product, you'll find some information on the product itself. For instance, the name of the product, the mode of data acquisition. Here you have a model, here a satellite. You'll also find information on the spatial resolution as such. Here, if it's a 3D product, three-dimensional product, you'll find the number of depth layers that you have in the product. Here, because it's a satellite, you don't have this information, as you can see. You'll also find the temporal resolution of the product and some of its variables. If you want to refine your search, you can use here the filters that are available here. For instance, because we want to focus on the Pacific, we need to select the global ocean area. Yes, we're going to choose, because why not, the daily temporal resolution as such. And then the current. You can either write velocity or current in the free text search bar, or find it yourself in the main variable here if it's available. So here we have all the products that fit this filter. As you can see, you have an in situ product, some satellite, and some model products. We are going to focus on the first one because it's the one with the most recent data. So when you click on the product, you'll be redirected to the product page with some overview on this product, some use cases, a little bit more information on the product. You'll find the notification tab, which gives you some information on the incident, improvement, and maintenance going on this product. You'll find the data access, with all the way you can download the data. You have the subset, the file, and the maps if you want to use it in QGIS, for instance. And under each section, you will find a little information icon. And when you click on it, you'll be redirected to, if it works, to an article of the Help Center that may help you use it. You also have the same thing for the dataset ID, because this will help you get the dataset that you need. For instance, here, those three datasets are about the current. This one is about salinity, and this one about temperature. And you can see here that this one has data for every 6 hours. This one has daily data, and this one has monthly data. You also have the contact tab. If you're facing any difficulty, if you have any issues, you can contact us here. You also have the documentation. So you have the product user manual, which contains some general information on this product, the quality information document, which is more scientific, related to the mode of data acquisition. You have a synthesis of the quality information document also available, and the license and how to cite this product. If you want to share this product, you can also click here, which will copy the URL that you can share. So we are going to add our layer to the map. So we wanted a daily velocity layer. So we are going to add it. Okay, so here we have it. To remove a layer, if you don't need it, if you don't use it, such as those two, you can just click on the arrows that are right here. Now we are going to add our net primary production layer. So we are going back to add layer. we're going to remove the filter that we had, still choose global ocean and daily for the products. And because net primary production is not present in the main variables, we'll have to write it in the free text search bar. So I'm going to write it. Sorry. Here we go. So here you have the three products that fit the filter that we had. As you can see, those two are a little bit hold the data in them. So we are not going to use it because we won't be able to compare the two. And we are going to use this one and just click on add in map right there. And we are going to add the daily net primary production as seen here. So here we go. Okay. So I'm zooming on the area. Yes, okay. So now I'm going to present to you the icon that are here. You have the download icon, which I'm going to present afterwards. The information icon, which will redirect you to the product page. The layer icon, which allows you to switch between variable in the same dataset as such. You have the gear icon right here. This allows you to change the visualization of of your layers. You can change the opacity of your layers. You can also change the color map if you prefer. You can invert that color map. You can also choose a discrete color map here. You can enter them manually. You can change the number of steps, decrease it or increase it. You can also choose to mask some data that are out of those range. For instance, if I write 1 here and I mask it, all the data that is not present in this range will be masked. You also have here an auto button, and this auto button analyzes the data that is displayed here and will try to fit it as such. So here we go. Because here we have a special layer, it's a velocity layer which contain vectors, which can contain vectors. You have this style option available. So you have solid plus vectors, or vectors. And we are going to keep it that way, so we'll be able to get a better look at the correlation between the two variables. This option is not present in every dataset. For instance, in the net primary production doesn't have this option. You also have the logarithmic scale, which again is not available with every product, but sometimes it can help with the visualization. Sorry, here we go. So now we have the time bar that is at the bottom. The thick white line represents the data that is available in the dataset. You can click on it if you want a specific date. You can also zoom in to be more precise, for instance here, and zoom out if you want another date. Sorry. Okay. You can also reset your bar once you're done, or if you want another date. You have exactly the same thing for the depth. So you can zoom in and out and to get a specific depth. So up is it. Now I'm going to present the features that are right here. So you have the point, the line, and the area. So as you can see, those will get you some graph on those objects. You can delete the graph that you don't need. You can also add some if you need. As such, you can also increase the resolution or export the sample to a CSV or a SVG. As you can see, you can only do that once you're logged in. So I'm going to do that right now. Sorry. Okay, so now you'll be able to export those sample. Keep in mind that, again, those are just sample. For instance, if you get it as a CSV, you will not get each and every day, but just a sample of the date that allowed the MyOcean to plot this graph. You also have the settings. In here, you can change the background of your map, as you can see here. You can also add the toponyms. You can change the projection as well as the units that are displayed on the map. Here we go. And here you can see some of the toponyms. Now I'm going to present to you the download option. I'm going to get rid of some of those objects here. So you can download whatever you want or you liked or you need. So you have the geographic area that you have to put in. You can either enter it manually or define on the map as such, or even take an already constructed object as such. You also have to choose your date range. Here you have the available date range in this data set, which will help you choose. You can either enter it manually or using the little calendar here, or use the as in map option as such. And you have the same thing for the depth. So here you have the available depth. You can either enter it manually or as in map. Here you have the weight of the file that you want to download. You can just click here and it will be downloaded. You can also choose to get the original file for this data set by clicking here. This will give you access to the file for a specific day for the entirety of the Earth and all the depth and all the variable in this data set. You can also click on the automate button, and this will generate a query that you can use to download the data on your computer by yourself. You also have some links that will redirect you to some article in our App Center. So keep in mind that the weight can't go over 1 gigabyte. If you do so, you'll get a message as such. As you can see here, a red message, and the link will okay, it's not working. Okay. The link will redirect you to all the ways you can download those data that are not right there. If you're facing this difficulty, you can contact us without any problem. To do so, you just have to click on talk to an expert. And if you go here, you can contact us directly and tell us that you have an issue or not. I strongly advise you to use one of those queries to share it with us. You can click here to share the query and copy it here, and we'll try to download it for you if it's not too large. You also have the help in this little pop-up. This will give you direct access to our help center. For instance, if I write MyOcean, you get all the articles that are on MyOcean. For instance, the introduction to MyOceanViewer which will have everything that I talked about today. And at the end of it, you'll have a Q&A with our most common question. You also have the news on the Copernicus Marine Service if you need to. If you want to share your work, you can use the button that is right here. You can share it via link, image, video, or embedded if you want to use it in a website. And you also have this little icon, information icon, which gives you information on the MyOcean itself with some keyboard shortcut, the credit, etc. So this is all for me. Again, if you have any question, don't hesitate to contact us. We're here to help. Thank you.
Thank you, Gael. Thank you very much for your demonstration. That's really nice. I think we don't have any questions for you till right now. If anything comes up in the rest of the session, we'll certainly address it. Thanks very much.
Thank you.
And now we will jump to the opposite coast. We go to the east coast of South America, and we will take a look at another a very interesting case study that was developed as an exercise, and it would be presented by Álvaro de Pascual Collard, who developed an exercise using a Jupyter notebook. Yeah, welcome, Álvaro, whenever you want.
Hello, Andrea.
Hi.
Good morning for the people in America. Hello for the people in the rest of the world. Let me share my screen here. Can you see my screen now?
Yes, yes.
Yep. Well, here I'm going to present the Jupyter notebook we have proposed for this workshop. In this tutorial, we are going to make a multidisciplinary analysis of the Amazon River plume. Well, here first I would like to remind you how to access the notebook. The notebook in the web page of the course, you will find in the upper tags a tag called Jupyter Notebook. So you have to click on there, and you will go directly to the page with the links for the Jupyter Notebook. We will see this later. And here you will have access to the notebooks. And well, in the notebook, it's important to know that is created in the environment of Jupyter Hub. So you will access a workspace like this, where you will find the notebook. Now I'm gonna show you this workspace. It's very important to remind for any user that first of starting to work with the notebook, you have to copy the notebook to your home directory. In this notebook, we are going to, as I said before, we are going to present an analysis of the Amazon River plume. But I will explain this directly from the notebook. Well, in the notebook, you will find different things like documentation and also cell codes, where we are going to do two main things. We are going to download data from Copernicus, from different sources, from both Copernicus services, and we are going to propose some different functions programmed in Python language to generate different plots. In these functions, we are going to work with many different Copernicus products. For example, model data. We are going to use products generated by model data for both types of models, physics and geochemistry. And we are going to see the variables of temperature, salinity, primary production, oxygen attenuation coefficient, which actually is the turbidity of the water. But we are going also to see other sources like remote sensing data. We are going to study the surface temperature and also chlorophyll from the ocean color tag. And also we have included information of the temperature and salinity produced by in situ observations. Well, going directly to the link of the web page, as I said before. Okay, you have to click in the Jupyter Notebook tag. And here you have some options, so you can read the guidelines to run this notebook, etc. And also there are some options to download the notebook. And also there is a link to register in Copernicus Marine Services. It's important to have in mind that you need to be registered as Copernicus user to run these notebooks. And well, clicking here, you can go directly to the Jupyter Hub access. And here you have to log using your own Copernicus credentials. And well, with this, you enter into the Jupyter Hub workspace. This is the workspace I told you before. You have a file browser here where you can find different directories or your own files. And as I said before, it's very important to copy the tutorial into your home directory. To find the tutorial, you can navigate through this link, through this folder, Jupyter Notebooks. Everyone should have this folder. And here you should find the Jupyter, the Training South America folder that has the tutorial. But please have in mind that you cannot access this tutorial in this folder because this is just a storing folder. So it's important to copy this tutorial into your home folder. Your home folder is the folder that appears when you click here in this little gray folder. So to copy this folder into your home directory, we are going to use, you can open a terminal here. This is the proper workspace of Jupyter Hub. And this is a terminal, a Linux terminal, where you can use Linux commands like, for example, $, to see the different directories. And for example, to copy the tutorial you need, you can use this command, copy -r, and you can use the directory Jupyter Hub and Training South America. And the destination of this copy is dot, which means the location where you are now. So when you do this, here there should appear a directory. Well, you can see here there appeared the directory of the Training South America, the training tutorial. But since here I have another one that is just a copy that it's already run. So we are going to open this, or I am going to open this, and I'm going to navigate through the tutorial to show you a little bit what are you going to find in the tutorial. Well, as I said before, these tutorials contain some documentation about the environment of the plume of the Amazonas River. This plume behaves following two main features. The first one is the currents present in the region, the North Brazil current and the North Equatorial current that transport properties following the coast in the beginning, but after that there is a injection of the properties in the inner ocean following the North Equatorial countercurrent. And there is also another path of transports that is the creation of eddies in this region that are transported following the bathymetry towards the Caribbean Sea. And well, the tutorial has, as you can see, some cells that you can run by clicking the button, the run button up here, for example. And here you should find an asterisk, and when the cell finishes to run, there should appear a number, which is the identification number of the tutorial, of the cell. Right. Well, in this tutorial, we have different sections, 6 sections, but the main sections are these 4 sections, the middle ones. In these sections, we make a tour over different Copernicus products, and we provide a view of the many different products that you can access through the Copernicus services. And also, to access these products, we are using this Copernicus Marine toolbox. This is a library developed by Copernicus services. It's a library that allows users to access the data directly from Python using Python commands or command line, so you don't have to access continuously to the web pages, clicking on the data you need. So you have a lot of options to automate your procedures, right? Well, in this context, I will explain a little bit about the section 2, that it works with near real-time physical modeling data. this section has a first subsection, which is the data accessing. Actually, all sections are pretty similar. So all sections has a similar structure. At the beginning, they have a first subsection that is data accessing, how you can access the data. In that section, we are working with this Copernicus Marine toolbox. So we use this function from the Copernicus Marine toolbox, the subset function, which is very interesting function and simple. So you can download data from many different sources and for many different variables in the ocean. And once we download the data we need for this section, for this source, in this case, the near real-time physical modeling data, we start to propose different cell codes to analyze how the data are stored in the files downloaded. And also we propose some cells to plot the data. In these cells, we propose three main functions that are the plot map function. It's a function that allows any user to plot maps of Copernicus data. So this is a function, this is a block that you can copy in your own computer, and it should work in the most of the cases, depending on you will only have to change this latitude and longitude names. So you will be able to create this kind of maps. For example, this map of salinity, surface salinity in the vicinity of the Amazon River. And analyzing the structure of salinity and the formation of the plume along the North Equatorial Contact Current. Well, after the proposal of the function of plotting maps, we also propose another function, which is the plot sec function. Is a function to plot vertical sections in a specific latitude. For example, here, so we can analyze the vertical structure of the Amazon River plume. For example, here we can see again the salinity. And also after this, we propose the new plotting function, which is plot Hofmöller, that creates a Hofmöller diagram in a specific location of latitude and longitude. And obtaining this kind of diagrams where we can analyze the variability of salinity in the vicinity of the Amazon River, so we can see the periods where the Amazon has more affect the river water mass, the fresh water masses affect this specific latitude and longitude, and study the variability in the surface layers. After each section, we propose an exercise. In this exercise, we also propose more or less the same exercise, which is to change the data set that we are downloading and also the variable. So we can modify all the code in this section. It's not very difficult. And it's also explained in the video tutorial. So if anyone has any problem with that, it can see how we do it in the tutorial. So you can change this code to download different data sets, and you can change these maps and plot different variables. So from here, you have the power of exploring everything you want. You can go to the web page, find the variable you are interested in and start to plot in your own maps. And after this is the final of the second section. And as I said before, the rest of the sections are pretty much the same, but downloading different data sets. For example, in the third section, we focus our attention in the near real-time geochemical modeling data. And here, obviously, we are not plotting temperature or salinity. We will focus our attention on plotting primary production and turbidity, and here we have again the same structure than before. We have a first subsection explaining how to access the data, how to download the data using subset function. And also after that, we have another section or subsection where we use these previously defined functions, the plot map function here. We use these previously defined functions to create our own maps, in this case, related with or created from biogeochemical data modeling data, right? Here, we create a map of primary production. Also, we create a vertical section of primary production, and also an Hoff-Moller diagram of primary production. We discuss these results and also propose some explanations of this variability. And in the exercise, we propose that to change the code, not to study only the primary production, but also to study the turbidity of the water using the specific variable KD, and downloading the specific data set for this variable. After that, if you don't want to use modeling data, we propose you can be interested in using remote sensing data, and we do the same again. We have a subsection where we explain you how to access this data using subset function, and also we use a previous function defined to create maps of, in this case, chlorophyll, right? Chlorophyll concentration. In this case, we are using, as you can see, a logarithmic color scale, so we get better results. And we can study the concentration, chlorophyll concentration in the vicinity of the Amazon River, and study the plume of the Amazon River. And from this section, since the satellite data doesn't have 3D data, we cannot plot vertical sections or Moller diagrams. So in this case, in this section, we only plot the maps of chlorophyll, and also propose to change the code to plot the maps of sea surface temperature here in this region. And in the last section, we jump into a little different product, which is the work with observational in situ data. In this case, we propose to download the information of an Argo buoy, an Argo profiler. So, as you probably know, the Argo profilers are buoys that are drifts with the current, so they are not static. They move with the currents of the sea. So, to download this type of data, we cannot use, unfortunately, the subset function, so we have to use a get function. So we explain you how to use this get function to download the data, and also to make two types of plots. For example, we can create a plot of the trajectory of the Argo float. So you can see the trajectory, where was the Argo, the float, and also the dates where it was. And also we create a kind of Moller diagram where we can see the profiles took by the float along the time. You can see, for example, depth and also the date. And this is our result. In this case, in the first case, we work with temperature, but we will see that we can also work with salinity. So we propose to rerun this exercise as using the salinity of this station. And well, this is a brief summary of the tutorial. I think the most interesting thing is that in this tutorial we are presenting how to download and work with many different sources of data. For example, we work with two sources of modeling data, physical and biogeochemical. We also use satellite products like the OSTIA sea surface temperature, and also biogeochemical satellite observations produced from Ocean Color. And also we also provide information how to start to work with in situ near real-time observations, right? As final exercise for people who is interested in diving into more knowledge and starting to work in depth work, we propose that, well, this exercise is done with all global sources, global products, global ocean. So all these data sources are provide for any place in the world. So you can we propose to use this exercise to change the code to run this exercise not for Amazon River, but other river, like for example, the Mississippi River we propose here, but well, you can use any river in the world or any place in the world. You just have to define the range of latitudes and longitudes where you want to work, the window where you want to work, and well, go ahead. This is the final of the tutorial. Well, I hope you enjoy it and you find it there lots of interesting information.
Thank you, Alvaro. Yeah, that was really nice, and I hope it sparked some curiosity for our participants to go and explore the exercises. We do have some questions for you, or at least 2 questions so far. The first one, these Jupyter notebooks were run on the Copernicus server. Is it possible to run the same notebooks from a local computer? So the hub in this case.
Yeah, it's perfectly fine. The tutorial is proposing the Copernicus server because it's easier to provide this tutorial. But there is options to access to download the tutorial to your own laptop, to your own personal computer. So in the Copernicus webpage, there is a link. When you enter into the Jupyter Hub webpage, there is some options. And as I said before, one of the options is how to download this tutorial to your own laptop. And in case you have installed the Jupyter system, this Jupyter interpreter, you can run the tutorial in your laptop. And also we provide inside of the tutorial, we provide as you probably know, you may need a file to create an environment to install the specific libraries you will need for this tutorial. But the file with the specifications and the configuration file that is needed to create an environment in your own personal computer is also included in the tutorial. So
provided, right? Yeah, exactly. That's it. Yeah, and as you said, Alvaro, we in the events page you will find the guidelines you will need to access the hub, which is temporary access. But then you also find guidelines to install your own Jupyter environment so you can continue practicing. And these tutorials will be available, or I mean, you already have a lot of tutorials available from previous workshops in the Copernicus Marine website in the area dedicated to the e-learning materials. And these tutorials, the current ones, will be available very soon as well in the same page. For the second question, how do I know which libraries I'll need to install to be able to use the Copernicus Marine data products?
Well, there is not a direct request. It's first of all is a recommendation. I think it's the best way to access the data. It's really fast. So it's from my point of view, it's the best way to access the data. But well, as Gael in the previous presentation explained also how to download data. from Copernicus webpage and from MyOceanViewer. So you can directly go to MyOceanViewer, use the information that Gael explained it before, and download the data you want to use. And from that data downloaded in NetCDF5, you can start to work with this Python code. As also said Gael, that method has a big weaknesses, which is that the limit of the size of the file you can download is just 1 gigabyte. So, oh.
Okay. There's another question that just came in. Are there tutorials for working with sea surface currents? I am sure we do have some exercise previously developed to use. I mean, we have a huge
according
collection.
what I can remember, you can go over tutorials. The tutorial we made in South Africa in the Agulhas current.
Yes,
it was
using
explained a lot about currents, and look for the tutorial in the Agulhas current, I think it is.
Agulhas, yes, I do remember seeing a few exercises with the currents. So I'm pretty sure. So I invite you all to explore our e-learning materials page on the Copernicus Marine Service. You will find a huge collection of exercises there. I think we are good in terms of questions for you, Alvaro. Thank you so much for your presentation and for this exercise. And now we will have the same topic, but this time using QGIS software. So you will see another perspective of this case study by Stefania Ciliverti. Hi, Stefania. Welcome.
Hey, Andrea. Hello, everyone. And thank you for this workshop and for being here to show you to complete the overview of the tools that we are proposing in this training session with QGIS. So let me share the screen. Okay. So I'll give you some as a sort of storytelling of the main steps that have been followed for the proposed exercise that you have seen in the video already loaded in the South America event training session in the Copernicus Marine Service. And as done by Alvaro, I'll focus on the Amazon River plume. So I'll give you briefly an introduction to QGIS and how to use the Copernicus Marine products. Then I'll move through a discussion about the implemented workflow that have been put in place for analyzing the data provided by the Copernicus Marine Service, a summary of the main results, and at the end I will give you some references in case you would like to detail some more specifically some scientific topics about this physical process that is related on the evolution of the river plume in the Amazon region. But before starting, I would like also to give a bit of a context where we are to conclude a bit this journey of 2 days that you have followed, because you, all of us, have been involved in understanding how, from the observation through the models, we are able to produce information that can be used for downstream services. And of course, when we talk about applications and services, we talk about tools that we need to develop in order to analyze the information that has been produced, in this case, by the Marine Corps Service, that for us is the Copernicus Marine Service. These are taken in from the ETUFS guide that is available in the Mercator Ocean International website. So these tools that we are talking about are needed for performing some geospatial data management, for analyzing the data, and also for producing science that is helpful for understanding the process of our ocean. And so this is what we are intending to do by exploring this second kind of tool that is the QGIS, that is a geographical information system. As a software, it provides basic but also more advanced functionalities for performing this kind of analysis of the ocean data. So you can view, explore the data, compose new maps, create, edit and manage the data as well, and finally analyzing them through some geospatial statistical tools. But on the other side, you can also publish maps on internet, so import them in your own application and extend the functions of QGIS through dedicated plugins. And in this training, we have been explored some of them. And finally, QGIS offers also the possibility to combine capacity of Python that before have been introduced by Alvaro with the functions provided by QGIS. QGIS, you know, it's an open source software. It's available, it has a dedicated web page, and up to now, we have two main reference versions. The last one, that is the 3.34, that is has been recently released by the QGIS community. And together with this, we have also the long-term release, that is the one that we used in this training, the 3.28. This can be, both versions can be installed in standalone mode, but if you would like to make also some developments of QGIS plugins, for instance, or you want to use more advanced capacity provided by this software, you can also install it through MyOceanViewer that allows you basically to install several versions of QGIS without encountering conflicts. So when you open QGIS, you will learn how to deal with the two major, let's say, kind of objects that QGIS is able to ingest. We have vector that represent the location and the shape of a geographical features using geometrical objects like point, lines, and polygons. And the QGIS offers a lot, I mean, many tools for making analysis of the data, as well as geoprocessing them and modifying it through subspecific geometrical tools. On the other side, we have the rasters that are made of pixels. So we have matrices of values that contains, that represents the condition or specific variables for the area that we are analyzing, and that is covered by this kind, I mean, this set of cells. And also in this case, QGIS provides a wide range of opportunities for analyzing, for making projection, conversion, and so on, or extracting also information. All the details about how to install QGIS are also provided through the Copernicus Marine event for South America training workshop in the link that you see in the slide, together with a short video that provides you some initial notes about how to install QGIS. But of course, linking and all the material is taking basically the information from the official QGIS web platform. At the beginning of my presentation, I was telling you that QGIS can also operate with plugins, so dedicated tools that the community co-developed for specializing, for instance, a specific analysis. In this case, in our training, we have done a quite large usage of this plugin that is provided by the Copernicus Marine Service, called the CMEMS Net, that facilitates the access and the loading of NetCDF files provided by the Copernicus, directly from the Copernicus Marine catalog in QGIS. by exploiting a very easy graphical user interface that takes as info the file that you would like to load by clicking on plus. And once you browse through the list of your products that you have been downloaded previously through the Copernicus Marine Data Store, you can visualize a refreshed version of this dialog window that will contain the list of variables that are included in the netCDF file, and you can add, for instance, like in this case, as a layer, the sea surface salinity for the region of your interest. This is the typical, approach for selecting and opening a netCDF file. And later I will show you some more dedicated examples on how to use it. Together with the CMEMS netCDF plugin, in our tutorial, we have also used 3 more plugins: the Quick Map service for loading a base map. In this case, we have a huge list like the ones provided by Google, Esri, and so on. But we have also 2 spatial analysis tools suited for selecting coordinates in a map, and this is the Lathlon tools. And this will facilitate you in the creation of the bounding box by simply identifying the coordinates and selecting it directly in the map for using as baseline for your polygon, and the terrain profile for extracting section or transects in an interactive way. The study area is exactly the same that has been presented by Alvaro before. That is the tropical Atlantic region, the Western tropical Atlantic region, that is characterized by a very complex circulation in the area of the Amazon River plume. And here, particularly in the QGIS training exercise, we will learn how to visualize the Copernicus marine data in the region, extracting the essential ocean variables values in some specific locations, and how to perform geospatial analysis for both physical and biogeochemical conditions in the Amazon River plume. Of course, as you have learned extensively in these 2 days, the Copernicus Marine Data Store provides the full catalog for the global product, that is the target product that we are going to use. And in particular, for this training session, we accessed the 2 kind of model products. The Global Ocean Physics Analysis and Forecast system that is provided by Mercator Ocean International, operationally, and we have been selected the sea surface salinity and the sea surface currents. Then we also accessed the Global Ocean Analysis and Forecasting system, again, that has been produced by Mercator Ocean International, and in particular for the biogeochemical system, we accessed the surface chlorophyll, the phytoplankton, and the dissolved oxygen, and 2 other products, remote sensing based, that are the surface chlorophyll at 300 meters and the surface chlorophyll at 4 kilometers resolution, provided by the Ocean Color Tag. So both you see below in the second row of this slide, that are one related on near real-time acquisition. So they are everyday, they provided through the Marine Data Store and as a, let's say, near real-time product. But we have also the reprocessed longer time series from 1997 that, for your knowledge, covers of course, the global ocean, and can be used, for instance, for performing some climate studies. The exercise that I'm going to briefly summarize here in this slide is related on the visualization of the Copernicus essential ocean variable, in particular, currents. So starting from the approach that I was showing to you at the very beginning with the Siemens NetCDF plugin, and as soon as you have been loaded in the QGIS through the plugin, the currents field provided by the Global Ocean Analysis and Forecasting System, you can exploit one of the functions, powerful functions provided by this plugin for the automatic calculation of the currents direction by using the option vectorize provided by the plugin as soon as you select both the U and V components from your NetCDF file. The vectorize function open another dialog window that asks you for selecting the U and V component that you would like to combine, normalize them for being used, for returning the currents field, and save the result in your local folder where you have saved your project. So at the end, you will visualize, as in the MyOceanViewer that was shown before by Gael, you can visualize basically the circulation for a specific, in this case for June 2023, of the currents in the Western Tropical Atlantic. And you will see the main patterns of the coastal current that are affecting and impacting the Amazon River plume. Another example that has been proposed is related on the visualization of scalar quantities like sea surface salinity, chlorophyll concentration in the region of interest, as well as phytoplankton at surface and dissolved oxygen. So the advantage of having this multiple source of information directly manageable through the QGIS gives us the opportunity for making some more, let's say, combined analysis of the content of the file, and specifically in the target region where you want to extract the information. And in this case, similarly to what Alvaro was showing before, also QGIS gives you the possibility through the terrain profile plugin to query directly your map by drawing in your map a section, and automatically for the layers that you have been selected, and that in this case are related on oxygen in blue, sea surface salinity in red, and chlorophyll in green, you can visualize the surface profile of the variables spanning in the along the section that is drawn in red directly in the map. And this can be, of course, used to explore content or monitor specifically and very easily taking the information on some specific region of your interest. But if you would like to make your analysis a bit more structured, in the sense that you know a priori which is the portion of coastal region that you would like to monitor, you can exploit the function transects provided by QGIS by simply implementing a workflow that is detailed in the video and also in the document that is available through the event platform. But here, what is nice to, let's say, is just to take as a message for future exploitation is the approach that we have been followed. Because at the end, to implement such complex features in QGIS, once you know which are the functions. So in this case, by selecting the input data, which are our layers, chlorophyll, oxygen, surface salinity, and phytoplankton, and by creating a baseline where you impose your section, by invoking the profile by lines, you can extract the values of your essential ocean variables in the given section you have been decided to generate along this baseline in the to the coastline. And the transect functions basically extrapolate from the raster that is related to the layers that we are analyzing, the values provided by the NetCDF, and they are returned as a table that can be queried or can be also exported for making additional manipulation in other environment, like for instance Python. So it's quite easy in this case, analyzing multiple levels of information by just using one tool, that in this case is transects. The third exercise instead shows a bit more in detail some processes, at least starts to present you how QGIS can be also helpful for extracting some scientific information from your NetCDF. And in particular, what I proposed in this tutorial is to focus on the pattern of salinity in June 2021, during the most extreme event, flood event that occurred in the Amazon catchment, and in June 2023, that, as we all know, is characterized by a prolonged droughts. So, by accessing the sea surface salinity that we have in June 2023 and June 2021, and by making a difference of these two fields, we can compute, using the raster calculator, the sea surface salinity anomaly, let's say, with respect to difference, with respect to what we had in the past as a reference value, in this case for June 2021. And the same kind of, let's say, you can automatize this kind of analysis also by using the model designer that is provided by the graphical modeler. That is a tool provided by QGIS that can compute anomalies for any kind, in this case anomalies, but you can use for any kind of arithmetic procedure in an automatic environment by just defining the workflow, and using, in this case, as I've done before, the raster calculator, you can compute the differences or the anomaly with respect to a reference climatology, and extend this approach, this workflow, to all the files that you need to process. In the example, I just proposed two timestamp for the two reference months. And as you can see here, this is the result of the difference of sea surface salinity between 2023 and 2021, where you can visualize the status of, let's say, the saltier waters that are characterizing more than particularly the 2023 with respect to you had seen in the 2021, when there was the impacting extreme flood events. The QGIS offers the possibility also for extracting contour lines from a raster field. This is done by using the contour function in order to have the isolines, so the line on the map with constant values, in this case taken from surface salinity, in order to visualize the area of influence of the Amazon River plume that literature considered to be below 35 PSU. And this is done by implementing very few steps are related on the selection of the layer to process, the capacity, I mean, the filtering of the specific contour lines that have been extracted through the contour function provided by QGIS. And in this case, as shown in the last map, you see basically the region characterized by salinity that is below 35 PSU. And this is quite, from the visual point of view, it's quite effective, because you can overlap. In this case, we have the two timestamp before have been introduced. So the surface salinity in June 2021 and in June 2023, and you can appreciate how the area of influence of the Amazon plume has been, let's say, was characterizing the Western tropical Atlantic region. In blue, you have the area impacted by the plume in June 2021, while in red, you have the one in June 2023. And you can perform some zonal statistics, for instance, for extracting some basic information about the averaged quantities in this region, in both regions. And this is done again by implementing a set of steps that requires the transformation of our raster of reference, that is the sea surface salinity layer that I was showing to you before, to vector, in order to compose, to have the composite of polygons that characterize your raster map. As soon as you have converted your raster to a vector, you can set up the query for selecting the region that is characterized by salinity between 0 and 35 PSU. And as soon as you have created, filtered them, you can select the region of your interest where you would like to concentrate your analysis and compute the statistics by performing simply clip. And I'll show you basically let's say the final step in this slide. So from the envelope of contour lines that are characterized by sea surface salinity that are in the range 0-35 PSU, you can, for instance, create a polygon that in this case is focusing on the delta of the Amazon River. And by invoking the clip by mask layer, you can just clip all the yellow region in the specifically in the area where you have the pink one, and obtain for salinity in this case and chlorophyll concentration the maps that are characterizing specifically the conditions, the sea state condition in the delta, and compute some basic statistics like mean, standard deviation, minimum and maximum value, variance, and so on, using the zonal statistics. So this is another way for making the analysis of your region of interest more peculiar, more specific, where you would like to perform some geospatial analysis. And through the zonal statistics, you can retrieve some averaged quantities that can be used for monitoring, but also for validation exercises. All these are extensively described in the video. Of course, here the main concepts can be, let's say, summarized in these few bullets. So the main message is that QGIS, similarly as, but of course with its own differences with respect to Jupyter notebooks or the MyOceanViewer, provides some additional way for analyzing the Copernicus marine products and extract some relevant statistics from these files. Functions like the raster calculator, but also transects, contour, offer the possibility to execute automatically numerical algorithms, for instance, for calculating anomalies over a given period, or for extracting contour lines that can be used for detecting the region of influence of the river plume. On the other side, you can also evaluate with QGIS the possibility to extract raster value over assigned shapefile with irregular geometry, like the irregular polygon that I was showing to you in the delta, in the region of the delta. And with the zonal statistics, you can compute very easily some average quantities and export these kind of values also in other format to be then ingested, for instance, in Python codes or in your operational chain. And here I'll give you some a brief number, very few but meaningful references that I've been used for preparing the exercises, together with a link again once more to the to the Copernicus Marine e-learning corner, where you will find all the information about the QGIS exercises. Thank you for your attention.
Thank you, Stefania, for your presentation. That was really nice, and we all saw that there's a lot to do with QGIS as well. That's a very interesting exercise, and as Stefania said, all this exercise and others are available. You also have a full demonstration of the exercise in the events page, and the specific documents related to the exercise. So please don't hesitate to practice. We don't have any questions so far. I think your presentations were super complete, or maybe our participants didn't have time to practice the exercises before. But please do practice and take advantage of these wonderful exercises that were developed on purpose for this workshop. Thank you very much, Stefania,
Thank
and
you.
to all of you.
Thank you, everybody.
So we reached the end of this workshop. I hope this was interesting for you. I hope you could learn a little bit more about what Copernicus Marine Service offers in terms of data, in terms of information, and other information or things that could be useful in the South America region. We hope you could have you could learn with some of the direct applications we showed yesterday and today. Before we go, I just wanted to ask you to take a few minutes of your time to fill in the survey we made for this workshop. It would be wonderful if we could know what you think about this format of workshop, what you thought of today's session related to the content, to the format, to everything. You could share with us. That can be very useful for us to improve. And yes, thank you all for your your presence, and I see you in the next workshop. Have a good day, everyone. Bye-bye.